So far, we have almost 44 participants in BBB. I think I'll better start right away. Right, let me start the recording first. And then share my screen. Okay, before I proceed with the remaining part of chapter 7 content, okay, let us do some revision first from last week, entropy. So guys, starting from last week, basically, you have started to make use of a new property which is called the entropy, right? And then how did we manage to come out with the working definition and also equation pertaining entropy is by make use of Clausius inequality here. So from Clausius inequality, right, we have considered uh, two combined cycle, which is made up of one reversible cycle device and also the system and the expansion of a gas inside the system. So by performing necessary energy balance, right? So we have come out with this particular equation of delta QR minus with delta W combined system, which is made up of the system itself plus reversible, equivalent, and delta change in total energy of the system. Now, from there, we have taken into account from thermodynamic temperature scale, right? Based on this particular diagram, and you have delta QR supplying heat to the reversible cycle device, and then it convert part of the heat received into work reversible and reject some part of the heat into the system. So from there, you have this relation, delta QR over delta Q equivalent TR over T, right? So from here, you have simplified to make it into this particular form. Now, we substitute this thermodynamic temperature scale into the energy balance that we have from the previous slide. So you have this particular expression. Okay, now when you have a cyclic integral or cyclic devices, so what happens is that the right side equation here is equivalent to zero, because if you check from your previous slide or from previous chapter, we have proved that the change in internal for the cyclic device must be equivalent to zero. So that's why we slash out the right term over here. Okay, so now what's left is the WC equivalent dr times cyclic integration of delta Q over T. Now, if we look closely again from this particular arrangement, all right, uh, this particular arrangement actually already violate the Kevin Planck statement, right? So when it violates the Kevin Planck statement, right? So what happens is that it cannot be the work done total. It cannot have a positive value. So that's why when we take into account if your WC cannot have a positive value, so we have contemplate whether it can have a negative or even it can have a zero value in order to satisfy the the Kevin Planck statement. So from there, and we have managed to come out with inequality condition, whereas your TR is always positive because this is your punya the thermodynamic temperature scale, which is always have positive. So from there, as you can see, your cycle integration of the Q over T is always less than zero. Okay. So now, in order to find the new property definition for this particular delta Q over T, which is equivalent or less than zero, So what happens that we know that basically if the system itself undergo an internal reversible, that means there are no irreversibilities present. Okay, the right side equation here must be equivalent to zero, right? Now, what happens that when we try to relate on any existing properties that we have from other previous chapters. And for example, if we try to relate that with W, okay, we know that basically your W net will become zero, right? So this is cannot represent your W net. Kalau the W net is zero, that means any working equipment such as turbine, compressor, and so on, and it will not give you a value of positive over there. So that's why it is impossible to be zero and impossible to be your punya W net. Now, if we try to relate with some other property, for example, change in volume, right? So from expansion and then when you compress to revert it back to its initial state. So again, the resultant for the delta V will give you zero. So again, you cannot have delta V applied in this particular new definition. So during that time, what happened? Clausius, he has mentioned that since it cannot represent any existed property value, so it has to be come from a new property definition, which is called entropy S. So that's why entropy has simply defined that delta Q over T for internal reversible must be equivalent to delta S of entropy, right? So this delta S actually represent the change in entropy system between initial or final, and then this is the delta Q over T integration during the entire cycle. We also have take into account on the special case under internally reversible isothermal heat transfer process. And this is very important, especially when you have thermal energy reservoir and that can absorb and supply heat indefinitely at constant temperature, because we know for any thermal energy reservoir, um, it has high or large energy capacity. So that's why your delta T is constant throughout. Now, from the increase of entropy principle, we have take into account from state 1 to state 2, and this process is reversible or irreversible, whereas to restore the system back to initial state, to state number 1, okay, it undergo an internal reversible. So when you expand the system, this is how the initial equation looks like. Now, we know this second part here represent your internal reversible, that what we have earlier from our definition. So when you summarize that, you come out with this particular equation of delta S is greater or equivalent to delta Q over T. Okay, so the left side equation represent entropy change, whereas on the right side represent the mechanism of entropy transfer by heat transfer, because you are the delta Q over T from there. So now, from this inequality, it indicates that for a closed system, during an irreversible process, okay, the entropy change is always greater than entropy transfer. Meaning that there must be like some sort of entropy is being generated or created and during the irreversible process. So that entropy generated or created is called the entropy generation, right? So if you write down the entropy change of the system, okay, S2 minus S1 must be equivalent to the entropy transfer by heat transfer plus with Sgen. And remember that the ordinary S is not equivalent to your punya Sgen, right? So, and that's why, as you can see, you cannot find any value of Sgen from your thermodynamic table, but S, yes, you can find that from your property table. Okay. Now, in case of an isolated system, okay, so this is the original equation that you have. Okay, kalau insulated adiabatic, that means there's no heat transfer. So that's why this is zero. You have delta S for isolated is always greater or equivalent to zero. So this particular equation actually serves as the working definition of the second law. And this is known as the principle of increase in entropy. Eh? It stated that total entropy change of an isolated system is always increases, or in the case of limiting case of a reversible process, it remains zero. That means if you have reversible, that means this is only encountered during the ideal or experimental. Your delta S is zero. And whereas if you have an actual one, you punya delta S for isolated is always greater than zero. Okay. In case of pure substance, if you are handling with water type of steam that change phase or even R134A, you can simply find the value of entropy by referring to the thermodynamic booklet. Now, there is a special case which is called isentropic process here. Now, under isentropic process, okay, what happens is that if this is your turbine, okay, and we know that turbine will produce maximum or highest net work if there are no irreversibilities present within this selected control volume or boundary. And if the equipment is insulated, that means there's some sort of layer covering up the equipment to avoid any heat transfer between this control volume and the surrounding. So what happened? This already satisfy to be called as isentropic process of steady flow devices. Okay, so when you have isentropic process, what happens is that your entropy value at the inlet must be equivalent to the entropy value at the outlet. Okay, so we already take into account example 5, how can we simply solve the problem if you have an isentropic process. Okay, and then when we have property diagrams, we know that one of the axes must be presented in terms of entropy. In this case, if you look from H versus S, you punya S ni, which is at the x-axis, right? So the value of delta S actually is a measure of irreversibilities present and during the process, whereas your delta H represent the amount of work produced or consumed for that particular device. Okay. Also last week, we have take into account on the TDS relation. And how do we get this TDS relation? It's all started from your energy balance of a closed system. U net minus W net equivalent and delta U. Okay. So from there, uh, we know that basically from our definition of entropy, okay, delta S equivalent delta Q over T for internal reversible. Okay, in the case of expansion or compression process of a closed system for gas, so we know that the W net out equivalent to P times delta V, and because of the boundary work that we have. So substitute these two equations into your energy balance, right? So you will end up with TDS equivalent delta U plus P times delta V. This is called as the first TDS or the first Gibbs equation, right? Now, The second TDS, we can obtain that by again performing energy balance, but this time you consider control volume or open system, right? So kalau you have control volume or open system, we know that we have mass flowing into and mass flowing out of the system. So this is the additional mechanism of heat transfer into and out. So from there, when you summarize, you actually have H equivalent U plus P times V. Right? So we differentiate this equation. You have this expression. Right? Now, you substitute this expression into the first TDS, then you simplify, you will end up with TDS equivalent delta H minus V times delta P. This is known as the second TDS equation, right? So obviously, if you want to find entropy change here for the open and the closed system, right, we can use either of this derivation that we have earlier, right? Now, let's take on the first case on the entropy change for incompressible substance, which is happening at the liquids and solid. So we know basically you have delta S equivalent delta U over T, right? Because you have incompressible substance. So what happens is that instead of expressing Cp and Cv, we can make use and the general C to represent the specific heat for incompressible substance. So that's why delta U equivalent C times delta T, right? So from here, from your first TDS equation over here, right? So you perform integration. We know specific heat is a function of temperature, right? So that means it must come from the average temperature between inlet, outlet, or initial and final state of the substance. And so that's why you have C average ln T2 over T1. Okay, so um, T average will give you C average from your punya table A2. You can check from your table, so that will give you a series of C, P, CV, or even C value for any type of substance. Now, in case of isentropic process, okay, remember kalau isentropic, that means S2 equivalent to your punya S1. In other words, this is equivalent to 0. So when you simplify this original equation, and so what we have discovered actually, you only left with T1 equivalent to your T2, right? So what we can simply conclude that, right, for the isentropic process of any incompressible substance, actually it is also undergo an isothermal process. Okay, so this is very straightforward. Okay, if you look from example 8, you have iron block, 30 kilogram of iron block, and 40 kilogram of copper block, both initially at 80 degree. They are dropped into a lake at 15 degree. Thermal equilibrium is established after a while as a result of heat transfer between the blocks and the lake water. Determine total entropy change of this process. Okay, now we know that delta S is actually made up between S of the iron plus delta S for the copper block plus also delta S for the water. And because you have three different bodies exist. So that means we know that when the iron block and copper block both at high temperature, when they are immersed inside the lake at lower temperature, right? So we know after for a while, the thermal equilibrium will be established between these two blocks and also the temperature of the lake, right? So to find entropy transfer, to find entropy change, right? So we have to evaluate individually what are the value of delta S for iron, delta S for the copper, as well as delta S for the water leak. Okay, now, as usual, when you are solving the problem, and you need to list down what are the appropriate assumption pertaining this particular example. So we know. Hmm, sorry, what is the question? Uh, any question just now? No, all right. Okay, now we both know eh, copper block and also iron block. Eh, these are incompressible substance. Okay, and then we can make use the value of specific heat C lah, at room temperature. Okay, there's no change in kinetic and also potential energy, as well as there is no work interaction. Okay, um, if you look from table A3, it will give you some limited value of specific heat for iron and copper, according at the room temperature. So if you look from table A3, and these are the value of C for iron and also the C for copper. Okay. Now, if you were to perform entropy change of the iron, right? Now, we know this is an example of incompressible substance. So that means we have to make use of this particular formula, C average ln T2 over T1. Okay, so as you can see, I am multiplying with mass in order to get rid of the per unit mass from this equation. So C average ni from your table A3, and then T2 basically is the temperature for the iron, and then the T1 is the temperature of the lake water, because lake water has very high thermal energy capacity. So that means the equivalent temperature, the T1 too, is maintained at 15 degrees. Okay, this is for the iron, and then you perform the same thing for the copper body, right? Guys, did you notice that you have negative symbol on both entropy for iron and copper? Can I know why? Hmm? Okay. Eh, some friend mentioned that both bodies are losing heat. Okay, yeah, that's correct. So now, as you can see here, when a system is losing heat, right? So basically, the entropy value also will become negative to show that the direction of the energy flow is from the iron and copper entering, into the lake, right? So that means you are the Q out, for both. Now, this is for the entropy change for iron and copper, right? So, like I said before, we also need to find the entropy change of the lake ataupun water from the lake. Now, how can we simply do that? Is by performing energy balance for closed system. Okay. So guys, as usual, if you perform energy balance, it is always recommended you start first from the basic equation. Okay, you are the Q net in minus W net out equivalent with delta U. And then we know there's no potential and kinetic. So that means what's left is your delta U, right? And then we know this delta U actually is made up of delta U for the iron and copper, right? Because the system is losing heat. So that's why you are the Q out. There's no Q in. Okay, so that's why you have minus Q out equivalent delta U for iron plus delta U for copper. Okay, now how to solve delta U? We know from any expression, okay, delta U by right must be equivalent CV delta T. But in case of incompressible substance, you can simply replace CV with general C times with delta T. Apply for both iron and also copper. Observe negative symbol on this side. So you bring to the right side. So what happened? That's why you have T1 minus T2 instead T2 minus T1. Okay, so when you simplify, so that means you have around 1,881 kilojoule, right? So delta S for leak, guys, if you remember, the isentropic, the change in the entropy for reservoir, and you are the equation of Q over T, where the temperature lake ni is normally constant at 15 degree. So from there, okay, this is amount of heat received by the lake, right? That means heat received from iron and copper enters the lake. It must be this amount divided by the temperature of the lake. So from there, as you can see, it gives you positive. Color positive, that means is accepting heat from iron and copper, right? So that's why if you find the entropy change of the whole process or system, it must be made up of entropy change for iron plus entropy change for copper plus also the entropy change for the lake. So like I said, since copper and iron, they are losing heat, that's why you are the negative symbol over there. Then the lake somehow is receiving heat, so it has mass positive there. So the resultant delta S for the whole process and will give you somewhere around 0.642 kilojoule per Kelvin. Right. Okay. You have looked on how can we simply solve problem using the entropy for incompressible substance. Now, if we have substance which exists in the form of gaseous form, and follow ideal gas equation of state. So when that happens, okay, there is a special case that you need to adhere to every time if you want to find entropy change for an ideal gas. Okay, now guys, from your first TDS relation, if you look from the original equation that you have for this one, so this is the first expression from first TDS, and this is from the second expression from the second TDS that we have derived earlier. We know du equivalent CV delta T, and then for gas that follow the gas equation of state, right, we can make use of PV equals to RT. So you substitute these two equations into the first TDS, you end up with this expression, CV times delta T over T plus R times delta V over V. Now, to find change in entropy, so we have to integrate. You bring that symbol sign to the right, so that means you have to integrate. That means CV is a function of T, bracket T, that means CV is a function of T. That means depending on T instead of pressure, right? Same thing also from the second TDS, dH equals to Cp delta T, and from the ideal gas equation of state, you rearrange back V over T equals to actually R over P. Okay, so from there, when you express the equation, and you have these two terms here. Now, there are two methods where you can apply to find the entropy change for gas that resemble ideal gas behavior. The first method, which is called the constant specific heat. And constant specific heat, that means you have to make use of Cp or Cv, right? And why does it call as approximated analysis? Because in order to utilize this first method, okay, we assume that the specific heat vary almost linearly with temperature range. All right. Um, that means if you have any calculation in terms of error, it can be simply minimized by using the specific values evaluated at the T average. So guys, if you check again from your first and second TDS here, right? So from your first TDS, you have CV average ln T2 over T1 plus R ln V2 over V1. From second TDS, you have CP average ln T2 over T1 minus R ln P2 over V1. Okay, so here it's up to you how can you simply make use of these two formulas and by checking what are the variables that have been provided. If you are given the specific volume value, so probably you might want to use this particular, the first TDS equation. If you are given the pressure value, so you might want to use the second TDS relation from there. Okay. Now, remember, this is for the constant specific method. The second method, which is called variable specific heats or exact analysis. Dah nama exact. That means, obviously, second method here is more accurate than the first one. Okay. Now, in case of your temperature change is too large, and probably we are talking about more than 100 degree in terms of delta T. And then the specific heat somehow did not follow linearly with temperature. So in that case happen, it is always recommended to use the variable specific heat in order to solve the problem. Okay, now, in order to utilize the exact analysis, okay, what happens is that from this second TDS relation over here, right, we know this part, the one in the bracket, we replace that in terms of S naught 2 minus S naught 1, where the naught zero value actually represent the absolute zero temperature. Okay, so when we replacing Cp as a function of T times delta T over T equivalent S naught 2 minus S naught 1. Okay, so when you replace this back into this equation here, and you have this expression, S naught 2 minus S naught 1 minus R ln P2 over P1. Okay, now, where to get this S naught 2 and S naught 1? This S naught value, you can check from table A17 for the ideal gas. That means kalau let's say your temperature T1, that must give you the S naught 1. Kalau T2, temperature will give you S naught 2 and so on from the table. And whatever that you define accordingly from this particular equation, right? So guys, remember under ideal gas equation of state or gas that resemble ideal gas behavior, you have constant specific method and also variable specific method. Okay. Now, what happened if the other gas somehow undergo an isentropic process. Okay, so when it undergo an isentropic process, now coming back from your constant specific method, this equation over here, and these two equation. So what happened is that kalau isentropic, guys, that means delta S here is equivalent to 0. Okay, so when become to 0, you will end up with this expression ln T2 over T1 equivalent minus R over CV times ln V2 over V1. Okay, now from this equation, you further simplify that. This is just using the apa tu calculus and mathematics punya value regarding on ln. So you want to have ln on both sides of equation. So what happened? If you have minus at the front of this ln, okay, so when you bring that into the power of something, so the V1 and V2 will change position, terbalik. That's why you ada ln V1 over V2 to the power of R over CV. Okay, so from there you can simply get rid of the ln. Okay, so what's left is your T2 over T1 equivalent V1 over V2 to the power of R over CV. Okay, guys, R over CV, we know that R can be expressed in terms of CP minus CV, whereas we know that K equivalent CP over CV. So when you simplify and you substitute these two into this equation over here, right? So that's why you will end up of K minus 1 to the power of K minus 1 over here. Remember, this equation here only applicable if you have isentropy. Okay, this is from your punya first TDS. Same thing also from your second TDS. From this equation over here, because isentropic, 0. So you simplify just what you have done from the first TDS, you will end up with this equation. T2 over T1, S equals a constant, that means isentropic. This is S equivalent kan minus. T2 over T1 for isentropic equivalent P2 over V1 to the power of K minus 1. So now you can see that between first and second TDS, the left side equation, they are equivalent to each other. So what we can do is by substitute the second TDS into the first TDS equation and simplify, you end up with this particular equation. So guys, from here, what we can simply summarize, your T2 over T1 for isentropic is equivalent to P2 over P1 to the power of K minus 1, and also equivalent to the V1 over V2 to the power of K minus 1. And remember, these three correlation here, they are only applicable if you have gas resemble ideal gas behavior, it undergo an isentropic process. Kalau non isentropic, you cannot make use of this equation. Remember, and of course, this is following the constant specific heat method. Right? Remember that these three conditions has to be satisfied in order to make use of this particular correlation. Right? Now, what happens if I have the variable specific heat that undergo isentropic? Okay, so guys, from previous slide, remember we have this particular correlation. Delta S equivalent S02 minus S01 minus R ln P2 over P1. And we have replaced the CP as a function of T2 in terms of S02 minus S01. So guys, what happened? This is equivalent to 0 because isentropic, right? So once equivalent to 0, right, when you simplify, let's say you have S naught 2 equivalent S naught 1 plus R ln P2 over P1. Okay, and I already mentioned to you from table A17, let's say kalau T 300 will give you S naught at 300, and then the T at 320 will give you the S naught at 320 with this value and so on. Now, from this equation over here, you simplify that, right? So you have P2 over P1 equivalent exponential S naught 2 minus S naught 1 divided by R. Okay. Now we want to have some sort of simplifying the right side of this equation. Okay. So when you break this down and then when you simply simplify that, you will end up with this particular relation. P2 over P1 as constant represent isentropic is equivalent to PR2 over PR1, where your PR is your relative pressure and it is given as the exponential of S naught over R from here that we have simplified from the above equation over here. Now, we can also express, instead of having the pressure ratio, you can also express this equation in terms of specific volume ratio. Where to get this? You make use of you punya PV equals to RT. Okay, so you take into consideration you have on both sides, kalau let's say you have P1 V1 equals to R times T1 equivalent to P2 V2 R times with T2. And when you simplify that equation, you will end up with specific volume ratio equivalent VR2 over VR1. Okay, so where to get all this PR and also VR? Again, from your table A17. Okay, guys, let's say, for example, if a process undergo an isentropic, you have been provided with pressure initial, temperature initial, and the final pressure of P2. The question wants you to find what is the final temperature of the gas when undergo an isentropic, right? So what you can do, basically, we know that from table A17, if you check, T1 will give you PR1 value, right? I nak cari T2, right? So since I am using relative pressure, so this is the formula that I can apply, right? So my PR2 equivalent P2 over P1 times PR1. So from the value that you have calculated for PR2, right, then you can simply get what is your punya T2 or the final temperature of the other gas. And probably you have to perform some linear interpolation on that. So guys, as you can see, you have gas that resemble ideal gas behavior. You have two methods, constant specific heat or variable specific heat. Each one of this method has its own formula. Okay. Now, if it undergo an isentropic, again, under constant specific heat, you have these three correlation that you can use, depending what variables have been given to you. And then under the exact analysis for isentropic process, right? So you can make use of the pressure ratio in terms of relative pressure or the specific volume in terms of relative specific volume. So make sure you know which equation to use for which method and that has been specified for you. Okay, let's have a look on this example here. Air, given temperature and pressure contained in the piston cylinder device, right? The air expand adiabatically until pressure is 100 kilopascal. Determine mass of air needed to produce maximum work of 1000 kilojoule. Now, the question already specified. It says, assume air has constant specific heat. And so that means we make use of the CVCP value. And so the name constant specific heat, that means we are actually solving this using approximate method. Okay. Now, as usual, air behave like an other gas with constant specific heat value. You check from your table A2, right? So you take the property of air at 300, which is at the room temperature. These are the CV and also the K value for your punya air. Now, the question wants to know mass of air to produce maximum work of 1000 kilojoule. Okay, so how can we use that? Basically, starting from energy balance equation. Guys, remember, you punya Q net in minus W net out equivalent to your delta U. Because this is a stationary system, you can neglect kinetic and potential, right? Now, we know that it's already mentioned and the air expand adiabatically, right? So that means you are the net work produced from there. Okay, we do not have any Q. So that's why minus W out equivalent with delta U, right? Now, we know that in order to solve the problem, you might wondering which equation that we have to use to solve the problem. Okay, because guys, from this expression, remember, minus W out equivalent M times delta U. Because we are using constant specific heat method, you cannot solve this problem by taking value of U1 and U2 from the table. That means you have to replace delta U in terms of CV delta T for constant specific heat method, right? So that's why you can see W out equivalent M times CV times with delta T, right? So now M equivalent the network out divided by CV times delta T. So I have to to find what will be the final temperature of T2 because T1 has been provided at 530 Kelvin. To find T2, I have to make use of this particular correlation. And remember this one. Okay, 2 over T1 equivalent to this particular V1 over V2 power of K minus 1. Okay, so from there, let's say T2 has this value. Then substitute inside your energy balance to get your answer. So probably it is close towards 8 kilogram of air. That's the mass of the air for the for this particular problem. Now, if you plot temperature versus entropy diagram, okay, you will have a straight vertical line connecting between these two states, because it undergo an isotropic process. S1 equivalent to you punya S2. Alright. Okay guys, any questions so far? Any part that you do not understand?
Excuse me, sir.
Yep.
Just now for the value of U2 minus U1, you said that we cannot take the value of U from the table. So for because you say that because the reason is because the question is about constant specific heat. So if the question is variable specific heat, then we can take the value of U2 and U1 from table.
Yes. Depending on
Okay.
what the question want, for example, kalau let's say there's no final expression on this one, there's no there's no assumption on this part. So let's say I remove this part, so that means you can solve this problem using any method that you want, whether the specific heat ke ataupun the variable specific heat, is up to you. Okay, any other question?
So for the question, if the question didn't mention the condition that just now the one you highlighted, the assessment, so we can use both method and the answer we get. Will the answer be the same?
Okay, good question. Probably not. For example, I already highlighted the importance of these two methods. For example, here, if somehow you have your CP and CV vary almost linearly with temperature, all right. Okay, so probably the difference in answer to between these two methods is not that huge lah. But somehow, let's say kalau your punya temperature change of delta T to is too large, I'm talking about a few hundred degree in difference, and then the CVCP is not very linearly, then you might want to consider the second method and so on. It depends. But obviously, kalau you stick towards that, you can see there's some slight difference in terms of your final answer. Okay, any other question? Right. Another 5 minutes. Let me finish this on the reversible steady flow work, and before we take 5 minutes break. Right, guys. From chapter 6 the other day, we have learned the importance of quasi-equilibrium. And we know that quasi-equilibrium can only existed when the system undergo reversible process. That means ideal. This quasi-equilibrium cannot be achieved in actual or in real process. But of course, real process, sometimes they are approaching or try to simulate towards quasi-equilibrium in order to minimize the effect on the irreversibilities. Okay, so now what happens is that starting from your energy balance for steady flow devices for open system. Because open system, we know one of the example of open system when you have steady flow devices, right? So remember, for open system, from your punya Q, sorry, from your energy in minus energy out, equivalent change of energy of the system, right? We know the right side here is 0 because you are the steady flow processes, right? The left side equation, which represent mechanism of energy transfer, you are the Q, you have W, as well as mass flow rate. Okay, so now when we expand the component of that, you are the delta Q reversible minus delta W reversible, equivalent delta H plus kinetic and also potential. Okay. Now, if we simplified this particular equation, okay, in the end of the day, right, what we have is V times delta P. Guys, how can I simply simplify from this equation into this one? Basically, you have to make use of definition of delta S equivalent to delta Q over T, for internally reversible. And also from your second TDS, you have delta S equals to dH minus V times delta P. So simplify these two, substitute into this equation. So what's really that you have in the end of the day is this particular expression, right? So you have W reversible in equivalent to the integration of V times delta P plus change in kinetic plus change in potential, right? We know if we encounter with incompressible substance, for most liquid and solid, okay, we can simply simplify that V times with delta P. That means you have to evaluate your P2 between final and initial state or final and initial condition from the value minus delta KE minus delta PE. So guys, what can we simply deduce from this particular relation is that your work done during the steady flow process is proportional to your specific volume. All right. It says here your V should be kept as small as possible during compression. This is to minimize your punya work input. That means W in, right? And as large as possible during expansion process to maximize your punya W out. Guys, remember, the reason why we're going to have expansion is to have work produced by the system. We want to have as large as possible W being produced, whether piston ready device ke, or even in turbine for control volume. And if you want to compress something, that means you are providing work to the system. So we want to keep it as minimum, we want to keep it as low as possible. And when you try to compress gas inside the piston, or for the pump or compressor that perform its job to transfer fluid from one point to another, or simply to increase the pressure and so on. So that is the main purposes of having turbine, compressor, and also pump. Okay. Now, how can we simply demonstrate the importance of this reversible steady flow work? Let us take compressor and also pump system. Okay, now from this example, it says that determine the compressor work input required to compress steam isentropically from 100 kilopascal to 1 megapascal, assuming that the steam exists as saturated liquid at the inlet state, and then B, saturated vapor at the inlet state. Okay, now we plot T versus S diagram with respect to saturation lines. This is the red one represent your saturation lines. Now, we know pump basically, pump handles fluid that exists in terms of liquid. Okay, so here what happens that from state 1, you have saturated liquid. Saturated liquid itu is still in liquid lah, but is at the borderline. That means at any time it will experience phase change. Okay. Now, state number 2 is at compressed liquid. Compressed liquid pun still in liquid phase, but somehow the property of the compressed liquid is very far away from the boundary. That means it will not somehow at any time will change into mixture and so on, because they are very far away from the saturated liquid line over here. So now, if we try to demonstrate the importance of reversible work between pump and compressor. Okay, so guys, starting from W reversible in equivalent integration of V times delta P. Okay, now we know because V is constant, because you have liquid. That's why I have V1 times P2 minus P1. Okay, so you refer from your booklet. Okay, V represent the value of V at your saturated liquid over here, right? So this is your punya VF, and then P2, P1. That means when you pump something, outlet of the pump must have higher pressure compared than the inlet. Okay, so 1000 minus 100. This is in terms of kilopascal, and then guys, this is the conversion factor. 1 kilojoule equivalent to 1 kilopascal times cubic meter, and need to be shown. So as you can see, the reversible work input for the pump to perform its job is almost 1 kilojoule per kilogram. Now, let's say we replace this pump with compressor. And then with compressor, we know actually it only handles gaseous form, gaseous form of fluid. Okay, and then we know, of course, compressor also is one of the devices that undergo an isotropic process. Okay, so guys, again, starting from your W reversible in equivalent integration of V times delta P. Okay, but now what happens is that from your second TDS, guys, TDS equivalent delta H minus V times delta P, from second TDS equation. All right, now isentropic because you have insulation layer covering up the compressor. So this term here is 0. So that's why you are the delta H equivalent V times delta P. Okay, so we are replacing V times delta P with delta H, right? So guys, H2, H1, yeah, from table. Okay, so H1 here is at, as you can see, H2 is superheated, whereas H1 is at saturated vapor. Okay, so now guys, when you solve the problem, you can see that the reversible work input for compressor is this much. Okay, now my question is, which one perform better? Hmm? Guys, between pump and compressor, which one perform better? You said pump, why? Okay, okay, remember back. Here, and for your pump, this one for your compressor. Okay, pump work is lesser than your compressor work, right? So here, what you can see that because pump only handles liquid, and liquid is incompressible substance, that means it will not encounter phase change, right? So having constant V will result small or less work required to transfer the pump from one point to another. But for compressor, as you can see, inlet is at saturated vapor, outlet is at superheated vapor. So you have phase change taking place. One superheated, one saturated vapor, right? So when you have phase change, the result from that will give you higher value of work required or work input, which is not a good idea or not a good result from this one. So that's why it is easy to pump liquid from one point to another because pump most likely will require less work input compared than compressor, because compressor normally will encounter different phase between superheated vapor and also saturated vapor. All right. Okay, we take 5 minutes break, guys. All right, let's move on to the isentropic efficiencies of selected steady flow devices. Okay, we did notice that most steady flow devices, eh, like pumps, compressor, turbines, even the expansion valve, eh, they all operate under adiabatic condition. That means well insulated. And of course, the other process for these devices, they are considered to be isentropic, meaning that there are no irreversibilities present within the control volume of these devices. Okay, so we can make use of isentropic or adiabatic efficiency, which is defined as a measure of deviation of the actual processes from the corresponding idealized one. Okay. Now, if we look at the first case, the isentropic efficiency of turbine, okay, we know that uh, under steady operation and the inlet state of the working fluid, whether you have steam, you have refrigerant 134A, or even if you have gas that enters your system, yeah, the initial state of the working fluid normally they has been fixed. Same thing also at the outlet pressure of those processes. Okay, so the ideal process for the adiabatic turbine represent the isentropic process between the inlet state and also the exhaust pressure, right? So isentropic efficiency of a turbine is defined as ratio of the actual work output to the work output that will be achieved if the process between inlet state and the exit pressure were isentropic. So when we represent this in terms of equation, right? This is the symbol of isentropic efficiency at T for turbine equivalent actual work turbine divided by isentropic work turbine, which is equivalent WA over WS. Remember, subscript A represent actual, subscript S represent the isentropic. Okay, so here, if your actual work turbine is closing towards your WS, that means your turbine work actually approaching towards your isentropic. So that means your punya isentropic efficiency of turbine should have higher value, right? So if we represent this in terms of actual and ideal, guys, please have a look. This is for actual. This one is the ideal. Okay, more or less the same. Okay, except that for the ideal, you have isentropic process where the outlet entropy is equivalent to your inlet entropy, which is related by the S1 equivalent to your punya S2, right? And of course, your turbine must be well insulated in order to have an adiabatic process. So from equation, isentropic efficiency for turbine equivalent WA over WS. Okay, guys, my question, how can I get this equation? How can I get this? How to get H, excuse me, how to get H1 minus H2A or H1 minus H2S? How can I get those? Anybody? Energy balance. How can I simply reduce into that terms? Okay, of course, from energy balance, right? So guys, when you have, okay, from energy in minus energy out, equivalent change of energy of the system, this is zero because steady. Okay, so what's left is your rate of energy in equivalent to rate of energy out. Okay, now we know that on both sides of equation, you are the Q, you are the W, and also the mass flow rate, right? So after we have take into consideration, on both sides of this energy component, okay, so obviously this is a turbine. That means turbine produce work. Okay, so from here there's no W in, but you are the W out. Okay, here you are the H in. On the right side you have H out. There's no Q, right? So that means your M H1 equivalent W out plus M H2. So basically you have this expression from your energy balance. So that's why you punya W out equivalent M H1 minus H2 over here, right? Because for actual, that means you put subscript A if this is isentropic, and you put the S symbol for that. Remember, isentropic condition is at the outlet of the turbine. Okay, so you have this particular expression over here. Now, if you represent this on H versus S diagram, all right, okay, this straight line represent the inlet and outlet pressure. Guys, remember, inside the turbine, you allow the steam to be expanded. So that means that's why you punya outlet pressure is lower than P1. That means your P2 due to expansion. Now, state 1 and state 2. State 1, H1. What happens is that if you have an isentropic, yeah, you punya state number 2 must be equivalent to your S to S. This is only for isentropic. Okay, but somehow if you consider the actual one, right, the value of H2A is lower than you punya H2S. Okay, so that's why if you want to calculate the WA, guys, if you look at from the distance between H1 and H2A, which give you WA, and then the difference between H1 and H2S will give you WS. Okay, so guys, can you tell me which one is bigger, WA ke or WS? Which one is bigger? Okay, of course, obviously the WS. Okay, work due to the isentropic process, right? Will have produce. So here, WS is greater than WA, right? So as you can see, this slight curve and dotted line, this represent your actual one. Okay, so that's why from here it is obviously we can see that WS is greater than WA. Now, for compressor and pump, okay, isentropic efficiency for the compressor is equivalent to isentropic compressor work divided by actual compressor work. Okay, WS over WA. Guys, it's easy actually to understand this. If you have the the isentropic efficiency for a turbine, which is expressed by WA over WS. So for compressor, basically, you just terbalik aja. It's upside down. Terbalik. You just simply change places over here. Right? So guys, again, WS, WA can be simply expressed in terms of H2S minus H1 divided by H2A minus H1. You carry out the same energy balance. So that's why you ada the M H1 plus W in. Remember, because compressor and pump, they require work. You are supplying work. That's why W in. Equivalent M H2. Right? So that's why you punya W in equals to M H2 minus H1. So depending H2S ke ataupun H2A from the system. Okay, this is H versus S diagram. Remember guys, when you are compressing something or you are pumping something, outlet temperature of the fluid increases as well as pressure. So that's why exit pressure P2 greater than P1. This is one of the important characteristic regarding on compressor and pump. Okay, so here you can see the difference between WA and WS. So guys, can you tell me which one is the good one, WA ke WS? Which one for compressor? Apa ni? Some say WA, some say WS. Okay guys, please observe carefully. Basically, you can see that WA is greater than WS. This is work input into system, right? Guys, this is not, this one is actually opposite from turbine. The bigger W, A, or even the bigger W is better. But somehow for compressor and pump, the smaller value of W is better, right? So that's why you can see here, and although your punya WA is always greater WS, so for actual pump or compressor, you need to provide the equipment or devices with more power or more work for it to perform its job compared than the one when it is operated under isentropic. Which is a bad news lah. Because guys, we know from apa ni, the other day, remember that from your heat engine system, right, where we have take into account the apa ni, steam power plant kan. Okay, steam power plant produce work. It generate electricity, right? We know that you need to have W net out, which is equivalent to W out minus W in. W out comes from W turbine minus with W in, W pump, in order to have clean W. Okay, so if your punya W pump is smaller, and therefore your steam power plant will generate more power based on this particular equation here. And so that's why under the isentropic compression, right, your WS must be always lower than WA, right? This is due to the presence of irreversibilities inside your control volume, right? Now, in case of the pump, okay, you can make use of the same formula, but somehow your WS can be simply replaced by V times delta P from the work reversible that we have derived earlier, and then you can solve accordingly. Now, under isotropic efficiency of nozzle, okay, defined by actual kinetic energy at the nozzle exit, divide by isotropic kinetic energy at the nozzle exit. So you ada V2A square divided by V2S square, right? And then how can we get this? Of course, it all comes from you punya energy balance. Okay, so here you punya V2A square, you have equivalent to H1 minus H2A, whereas V2S square equivalent to H1 minus H2S. Okay, guys, sometimes when the cross-sectional area of a nozzle inlet here is too large, right? Kalau the area here is too large, your velocity is becoming too small. So when it's becoming too small, you can simply neglect the value of V1. That means this V1 ni is actually equal to 0 because V1 ni approaching towards 0. So that's why you can put your V1 is equivalent to 0 in order to solve the problem and so on. Okay. And this is the H versus S, right? Almost similar to what you have with your punya turbine. Okay, on this example ni, guys, please have a look. I don't want to go into details because you can have a look on this example and then try to solve this during your free time. Okay, guys, any question? Because I am going to stop here for today and to make way for you to prepare for your quiz number 2. Do you have any questions so far? Okay, if not, that's all for today. Remember, you have quiz 2 start at 2 p.m. until I think Dr. Shafira opens until 5 ke 6 ke 7 p.m. for today. And so you have couple of hours to do. Quiz 2 is MCQ type of question, right? I think she has said I think 15-20 minutes. So please make use of the time given. Okay, guys. Since this Friday is Hari Raya apa ni Haji, so there is no lecture, right, or even tutorial. And then if we look from our apa ni planning on this course, somehow we are on track to finish on time. So next week, I'm going to continue the remaining part of the chapter 7, and on Wednesday, we can finish chapter 7 totally. And do not forget, next week also you have test 2. Okay, so test 2, this time the question has been set differently. It's not easy ataupun straightforward as what you have from test 1. Okay, it is more like open-ended type of question. So that means there is no single answer from each of you. Right? Right. So has to include what chapter? Until chapter 6. Second law of thermodynamics. Quiz as usual, 10 MCQ je. Until chapter 6. Of course lah, 5 and 6 to include part of that lah. Okay, how many chapter left? Only 2 chapters left for this semester. On the ranking cycle, and the other one is on the Brighton cycle. That's all. Both we can finish within 3 hours. Okay, guys. So thank you very much for your time, and good luck for your quiz this afternoon. Right, thank you. Right, thank you, and selamat Hari Raya. And those of you balik kampung traveling, please make sure you come back safely.